Good morning, everyone. Welcome to the EasyPower Thursday Technical Webinar. My name is Jim Chastain. I'm with the Applications Group here at EasyPower. Today we're talking about the newly released IEEE 1584 2018 version of the arc flash calculation standard. And I want to welcome you all for attending. Welcome to the event. And hopefully we'll be able to answer as many questions as we can as we go through this. So in general, I wouldn't say this is a comprehensive review of the standard. Primarily, I want to cover what has changed, what has not changed, what is new in the standard itself, and then how it's addressed in EasyPower. And at the tail end, as much as possible, probably the biggest question is how is it going to affect existing studies, and it's a little difficult to do that without having specifics. So we'll do what we can and hopefully share some guidance on your evaluation. So just as a quick bring you up to date, in 2002, the initial release of 1584 was labeled the Guide for Performing Arc Flash Hazard Calculations. It had an update or an amendment in 2004 and 2011, which were basically referred to as application notes and further explanation on how to apply the standard. And so it's been the better part of 16 years since we've really had an update to the standard. And as of middle of December 2018, the current version is official and in our hands are available for examination. It is recognized pretty much across the board as the de facto standard for arc flash calculations. This includes designation in OSHA standards, National Fire Protection Association documentation, the National Electric Code and the Standard for Electrical Safety, and then in the IEEE C2 National Electric Safety Code. So with that kind of introduction, I did want to conduct, if you will, a real quick poll question. And again, we appreciate the feedback, and it does help, if you will, our understanding of the audience and how we're serving your needs. And so real quickly, I'd like to gather some feedback on a voluntary basis. And let's start with how many studies do you or your company complete during the course of a year? And obviously there's no obligation to this, but we do appreciate the feedback. And here's how folks have voted on that topic. Thank you very much. And then the second question is how long do you expect to continue to use the older standard, the pre-existing standard? And this is a question that I guess is open for a lot of discussion, and depending upon which quarter of the market you're in, your response could vary quite a bit. And so part of our goal here in this presentation is to give some insight into the way that the standard has been implemented in EasyPower and give you some ability to analyze what that means in terms of the systems that you work on. Here's how people weighed in on this. Not surprising that there's a wide spread of opinions, and I, in a lot of ways, I sympathize with the situation that everyone's in, because there is a lot of, I don't want to say vague reference on how this standard is applied, but as everyone knows, it's referred to in the NFPA 70E version, which is frankly only about a year and a half old. And so it currently refers to the old document. So in 2002, the basis for the standard was on some 300 tests or so that were done in the late 1990s and the analysis made. And since that time, during the last 5 or 6 years, another battery of tests have been run, and consequently there's a much richer database to formulate the standard that's been presented, and consequently there's a little bit more gravity to it, gravitas, and as far as the application of the standard. I think that helps a lot of us in terms of how we weigh the material. The calculation parameters that were included in the 2002 standard included voltage, bolted fault current, and the arcing time, and then working distance, electrode gap, and then some fudge factors, for lack of a better term, that included distance factor, enclosure type, and system grounding. And what we see in the updated standard is that there's been more granularity taken to the enclosure type. And they being the IEEE committee, explained that the initial system grounding influence was on a limited test basis, and with further testing it was determined that system grounding had little, if any, effect, and the distance factor that was used has been expanded into more understanding of things like the electrode configuration and the enclosure size itself. So in those terms, it's, as I say, it's a much richer database, and consequently, as you'll see, we have the ability to expect better resolution and better accuracy as we get into certain parts of the spectrum. So let's talk a little bit about the range of the model. So in 2002, the voltage range was from 208 volts to 15,000 volts. There was a line of demarcation at 1,000 volts or greater where certain factors took place or were no longer used, and we'll get into that detail in a bit. With the updated standard, the range is still overall 208 volts to 15,000 volts, but the crossover point has been determined to be at or above 600 volts. And we'll see how these factors, and a better understanding of how the test results encourage this line of demarcation. Although the verbiage is very similar between the two documents, it was stated in 2002 standard that the model had the ability to predict the arc flash instant energy over frequencies from 50 to 60 hertz. That's been modified in the current updated standard, and very specific. The application of the standard is only at 50 or 60 hertz. It doesn't necessarily hold for frequencies beyond those two data points. Now, in terms of the fault current, it's still 700, well, it was 700 amps to 106,000 amps. Now that's been modified again based upon the 600 volt line. Below 600 volts, the range is 500 amps to 106,000 amps. Above 600 volts, the range is 200 amps to 65,000 amps. I'm not sure that that really impacts anyone negatively, but it does give us the ability to predict on a more accurate basis in both sections of the curve. So we'll have some data results here in a second. Probably the most interesting change in the model is the orientation of the electrode. In 2002, the electrode gap, or actually this is more accurately referred to as the air gap, ranged from 13 millimeters to 152 millimeters, and this was based upon the area where bare conductors came in the nearest proximity to each other. In the 2018 version, again below 600 volts, the air gap or the electrode gap has a range of 6.35 millimeters to 76.2, and this is affected by the type of equipment we're talking about. In above 600 volts, the range is 19.2 0.05 to 254 millimeters. So a broader range at the higher voltages and a slightly smaller range at the lower voltages. Again, giving us better resolution, frankly, on both ends of the spectrum. A couple new equipment types have been defined, which were not in the 2002 standard, along with their typical values, which will be included in the default the definition of the type of switchgear. And so we have 15K switchgear along with 15K motor control centers, and then 5K switchgear along with 5K motor control centers. There's also the inclusion now of a shallow panel board, and that has some interesting aspects when it comes to the amplification factor of radiated energy. And I think this was an area that was fascinating to me because it somewhat turned on its head my understanding of what reflected energy really amounted to. So we'll see those test results as well. Working distance, and this is one I'm going to reserve comment until later, but in 2002 there was really no range or limits as far as the working distance. So the model was apparently able to predict a working distance both very small and very long based upon whatever the incident energy was. In 2018, the committee has decided to only define or determine working distance at greater than or equal to 12 inches based on the assumption that if you're inside of that distance during an arcing flash, that you're within the plasma ball, and in which case everything would vaporize. So it didn't make any sense, in their opinion, to define that as a working distance. And more on that later. So the typical values then for different types of equipment and different voltages have been defined. Again, you'll see as we get into the tools, these can be modified based upon user inputs, but when you use the typical values for each of these pieces of equipment, the working distance is going to be defined and used in the calculations, if not changed by the user. And so again, there's nothing really new as far as the dimensions here other than the fact that we do have a separation between switchgear and motor control centers and then the shallow panel at the lower voltages. And so, as I mentioned, electrode configuration was the area where there were some surprises based upon the new testing done. And in 2002, it was recognized that there was an amplification factor going from an open air arc into an arc that was produced in a 6-sided enclosure. And that's been modified or amplified now with additional test results. And there were some surprises as far as those tests. So today we have a definition of vertical conductors, vertical electrodes in a closed box, vertical electrodes terminated into a barrier in a closed box, and then horizontal electrodes in a closed box. In the open air, now we're separating the vertical in open air and the horizontal electrode configuration in open air. And we'll again we'll see the test results, and this is one where we're not talking about gravity, we're really talking about the orientation of the operator vis-a-vis the termination of the electrode. So we'll try to amplify that a little bit as we get to the details. So here's the example that's used in the typical test configuration that was used even in the 2002 series of battery of tests. And this presumes that the operator is standing in the open area, and the vertical orientation is the bus work, and at this point it's not terminated in any sort of a barrier. And this is still the default of most configurations if we're not designated it by user input. The surprise entry into this discussion is the vertical electrodes terminated in an insulating barrier, because test results showed that there was rather than the arc traveling down, it actually amplified as it spread out, thus exposing an operator standing at the opening to more radiation if that termination was not there. And one example of that type of termination is a typical molded case circuit breaker, where we have the main feeder coming into the top of the system, and if an arc were to happen at that point, the arc would be basically spreading out or bouncing off of that barrier itself, the insulating barrier. So we'll see, the surprise was at how much higher this particular radiation was compared to the vertical termination that was being used as the default. And then finally, the horizontal electrodes in a metal enclosure. And again, the definition of this is left up to the person doing data collection and observing the equipment. But this type of an illustration or this type of an example might be a disconnect where we have the potential for having the electrified conductors coming out at us. For instance, if we were changing fuses for whatever reason in a hot box, and once an arc initiated on these terminals, the direction of radiation would be amplified because of the orientation of the electrodes. So this has been singled out or called out as a separate type of enclosure. Then in the open air configuration, again, this is basically defined as the operator standing from our perspective to the side of the electrodes, and there's no exposure beneath them. And if we look at the examples that are in the standard of the radiation pattern, it actually goes down more so than out at the operator. On the other hand, if we're talking about open air configuration for horizontal electrodes, the assumption is the operator is more in the proximity of the end of the bus terminations or the electrode terminations, and so consequently the radiation is directed more up at the technician or the electrician themselves. Now, this is not a gravity thing, that if I have a vertical oriented termination and I'm standing under it to make whatever adjustments I need to make, then I have more exposure. And in fact, this question's already come up from someone in the audience, that I would, if I were working under this type of a electrode termination, I frankly would categorize this as a horizontal electrode configuration in open air. Again, more because of the operator proximity rather than what the termination is actually doing. So again, this is set up because radiation is coming out straight at the operator, and this is the radiation is incident energy is being radiated down more so, and the operator standing to the side has some exposure, but it's not as much as if they were on or directly in the path of the termination. Okay, some data, and this is where the fun starts. So if we hold the voltage and the termination of the arc constant, and we compare the voltage fault to the arcing fault current for different types of termination, we see the highest pretty much over the whole band of voltage fault current to be the vertical termination into a barrier in a closed box. And then right below that is the vertical in a box, and then horizontal in a box, and then again the vertical in open air and horizontal in open air. So one might draw from this, if I have systems where everything is terminated into a barrier, then potentially my arc fault current will be higher based compared to what I calculated in the 2002 version. As far as the enclosed configurations for without terminations, looking at bolted fault, we compare horizontal instant energy calculations. Because of the higher current, the instant energy now becomes greater for the horizontal in a closed box, a little bit less for the vertical terminated into a barrier, and then the lowest instant energy versus when we're plotting against bolted fault current is a vertical in a closed box. Now, if we lay into that the calculation model of 2002, we see that it was pretty much middle of the ground and starts to exceed the current measurements, or the measurements predicted by 2018, when we get to the high end of the bolted fault current range. So again, it was, if we have horizontal in a closed box, the 2002 version was pretty accurate, whereas if we have vertical in a closed box, the 2018 version will be much kinder, I guess. We would expect lower instant energy as a result. Open air configurations. Again, if we're plotting instant energy against the fault current, the horizontal in open air yields a much higher radiation pattern because we're standing at the end of the bus termination, the bus itself, the electrodes themselves. If we plot that against the 2002 model, the 2002 calculations will be, for the most part, more conservative when we're looking at the vertical orientation, and less conservative, maybe not as accurate, when we're looking at horizontal orientation. So again, what the expectation here is, at least in my opinion, if we're working in a vertical electrode configuration open air mode, our calculations may be conservative if we're based it on the 2002 model. Okay, enclosure size, again, has replaced the distance factor multiplications that we were using in 2002. And it comes down to the height, width, and depth, primarily of the enclosure opening, and this will dictate a correction factor based upon the voltage and the dimensions of the cabinet. The enclosure size has been defined in typical values. Again, this is not much of a change, but now these calculations are going into the model by default, and so the operator or the person doing the analysis has to take some steps to modify if they have equipment different dimension-wise than what's listed as a default. And so we'll show that when we get into the EasyPower tools. These are controlled by the variables or the settings in the library, the default values. They can be adjusted and modified based upon what your particular needs are or systems that you may be working on frequently. And we'll see this when we get into the data, it's the shallow end of things that was a surprise, at least to me, thinking that there would be less, in my mind, less reflection than there would be in the larger piece of equipment. And so once I get into the tools, we'll look at the library entries, and it changes, or it will change as you select which model that you want to use for your standard. And this is a demonstration of the 2018 version and showing all the default configurations and dimensions. Okay, based upon the tests conducted, if we compare the instant energy radiated as over the height by the width of the opening, we see that compared to open air, the enclosed radiation is higher, especially up to 20 by 20. In fact, 20 by 20 is the highest multiplication factor or amplification factor, And once we get beyond 49 by 49 as far as dimensions, the difference flattens out. It's still a multiplication factor over open air radiation, but it's not as dramatically changed. So below 20 by 20, we actually have a shallow, we define that as a shallow enclosure, and surprisingly, that amplification factor goes down. When we look at how it's implemented in EasyPower, we'll see on the bus data dialog box, which we would select the type of element that will have an impact on what's being determined in the library. And then on the arc flash hazard tab, we will either use the default from the library in terms of working distance, electrode gap, configuration, and size, or we can specify by just hitting the radio button and making entries for working distance, electrode gap, if we know it's different than the standard electrode configuration. This is a point that I want to kind of make an issue of, and that is based upon a particular cubicle or bucket, there can be multiple orientations in the same enclosure, depending upon whether the feeder's coming into the top of a terminal or a plastic structure, insulating barrier, or if we have feeders going out the bottom or out the side. So again, that would be designated and separate from what's being provided as default from the library. We'll see that in the tool when I open that up. Now some of the nuances of the recommendation. In the 2002 standard, there was the ability to determine the arc flash boundary based upon a predetermined level of PPE. Never saw anybody, I never actually saw anyone using that feature, but in the 2018 version, it is defined or standard at 1.2 calories per square centimeter. So there's no adjustment factor allowed as there was in the 2002 version. In 2002, it was recognized below 1,000 volts that there could be a potential for a reduced arcing current to produce a higher incident energy. And usually the comparison was made between 100% arcing current and 85% arcing current. And then the tool was set up to use whichever was the more conservative and produce the higher incident energy. That's no longer adjustable, and the extension beyond 1,000 volts now is automatic. And you'll see on the curves when we get into the data that there is a potential for reduced current to have a higher incident energy, but it actually varies. It's not a fixed ratio as we go over this voltage range. And so it's applied basically in this mode. If we look at 100% arcing current over a range from the 208 volts to 15,000 volts, the reduced arcing current plot has the potential for producing more conservative incident energy. And if we compare it against the 85% level that was used up to 1,000 volts, you can see that we get more accuracy in terms of the reduced arcing current, in terms of variation of the electrical properties of the arc, and it carries all the way up to the full 15,000 limit. And it's reduced percentage-wise, but now the tool does this comparison for us automatically. It's not adjustable or programmable, and you'll see that the indication is made when we get into the tools with a different color ink when the incident energy calculation is made on our spreadsheet. So how that looks in EasyPower, in 2002, we had the ability to change that comparison between 100% arcing current and 85% or whatever other two values we wanted to enter here. In the 2018 version, that choice is not left up to us, and it will be reported in much the same manner as it was in the 2002 version. Now, we've talked about integrated method before, especially when we were talking about extended trip times and multiple complex systems that had multiple sources. And the question came up, well, if the integrated method as EasyPower implements it is a better, more accurate calculation method, why don't we use it all the time? And the justification was it wasn't part of the standard. Well, now with the release of 2018 and the verbiage that states systems containing multiple sources of short circuit current, such as generators, large motors, or more than one utility supply, and a good case in point is a PV farm where you have relatively low energy current that could supply a lot of energy. They need to be more accurately modeled with a dynamic simulation method. These methods may include multiple calculations to account for decaying short circuit current, current contributions from rotating equipment, and the effect on protective device opening times and the resultant instant energy. Which brings me back to EasyPower's integrated method. As you will find in the help system, when you look up the definition of integrated method, when it's selected as our calculation for current source, during the first half cycle, we use actually for the first cycle, we use momentary current to integrate the energy for that current. Then for the next 8 cycles, we use the 5-cycle current to integrate the energy that's produced. And then if the fault lasts longer than 8 cycles, the tool uses a 30-cycle current for calculating the instant energy. These are all summed, and consequently we refer to that as the integrated method. Now when we get to the tool, it shows up in the old version. If we selected 2000, and just a side note, you still have the ability in 10.2 to select which model you're using and make comparisons as you proceed. And so when we get into the tools, you can see I can kind of go between these two choices just by selecting whichever standard I'm going to use. But with the 2002 version, the recommendation was to use momentary current for doing arc flash instant energy calculations. We had the choice of doing an integrated method, but again, it wasn't necessarily recommended by the standard. In 2018, where the standard does recommend the dynamic simulation or calculation method, by default, when I start a new arc flash project, it will have both 2018 as the standard and integrated as the method for doing instant energy calculations. Arc sustainability. In the 2002 version, the verbiage was system voltages 240 volts or less supplied by 125 kVA transformer or less could be disregarded as sources of arc flash hazard. That's been modified to some extent, and now the verbiage in the 2018 says below or equal to 240 volts and less than 2000 amps voltage fault current, sustainable arcs are possible but less likely in this particular range. This was known as the low voltage exception in the older model, and some people claim that the exception has been removed, and in fact the verbiage is definitely more spongy, and we'll have subsequent discussions and webinars a little bit later to get into more detail on this. But for now, there is nothing tied to the low voltage exception that would include the ability to measure 125 kVA systems. There's just a need to be concerned about anything with greater than 2000 amps of voltage fault current, and then the need to deal with the fact that it's possible with lower current, but less likely in a three-phase system to have an arcing flash hazard. In 2002, the standard specifically says outside of the voltage range of this model, which was a 15,000 volts, we recommend using the Rauff-Lee method. In the 2018 version, they specifically don't recommend anything. They don't say not to do it, they just don't recommend anything. And so you'll see when we get into EasyPower that no results will be predicted for voltages outside of the 15,000 volts unless I take steps to deal with it based on engineering judgment. Where this comes from is a little bit based upon the accuracy of the model. So if we look at the incident energy over a bolted fault current, in this case to 106,000 amps, we can see 2002 model was a little bit more conservative, and then the 2018 version seems less conservative and hopefully more accurate based upon just the bolted fault current at that upper range. If we stay with the 2002 model, there's some potential that it's a linear progression of the results. And this is not a recommendation, this is just a statement of fact as far as how linear the model was. If we look at the plot for 2018, there's concern that it's not only less accurate, but if we get to a certain point, it falls off the cliff in terms of rational understanding of what incident energy ought to be at the higher currents, higher bolted fault currents. If we take a step back and say, well, what happens if we do consider Rauff-Lee method above that current range? The equations seem to predict a less conservative approach than 2002 and less of a concern in terms of the 2018 version falling off the cliff. But again, the standard itself does not make a recommendation. So we supply this just as a point of reference. It doesn't hold any water in terms of what your particular system needs to consider. And then, as I mentioned earlier, because of the lack of data at the time, with more test results, it was determined that the system grounding really had little effect as far as incident energy results, calculation results, so it's not considered as part of the 2018 version. The 2-second rule, it's one of my favorite soapboxes, which I'm not going to get on now, but it's still almost with the same verbiage, it still exists in the standard. And basically, the statement is 2 seconds is considered a reasonable maximum time for incident energy calculation in areas where we have extended or excessively high incident energy due to longer trip times on the protective devices. Now, it's recommended that we take into account and consider using engineering judgment based upon the type of work that's being done and the potential for any egress of an operator to be blocked while in the area. So again, there's still the ability, based upon this verbiage, to limit calculations to 2 seconds if for any reason they seem, I shouldn't say that, if they seem to be excessively high due to long trip times of the protective devices. Single phase. On the bottom line is nothing changed. In terms of the 2018 guide, it's single phase arc flash is not part of this guide, but there are some guidance and references provided, which to me sounds a little bit weird, but that's the way it states. I'm not passing judgment. Likewise with DC systems, the In neither case, neither the 2002 or the 2018 standard is arc flash part of the model, but again, there's references and guidance offered based upon the bibliography that's included with the 2018 standard. Back in 2002, the results of the regression or the curve fitting effort that was done with the database that was constructed at the time produced these 4 or 5 equations to be able to produce arcing current, incident energy, and an arc flash boundary. With the advent of the new standard, it's a multi-tier approach where we go through one of 3 or 4 different voltage levels to get an intermediate incident energy and arcing current, and then we plot those and interpolate for the voltage that we're actually using. And consequently, we go through multiple tiers of iteration and calculations, and then once we're done, apply specific correction factors based upon the type of equipment that we have. So what was a relatively straightforward calculation process using 4 or 5 equations, we now have something like a dozen equations that have to be reiterated anywhere from 2 to 4 times, and then correction factors applied to that, which pretty much negates the potential for being able to do this stuff by hand. So I offer these just as a point of reference, and certainly if you have an interest in giving it a shot, the standard delineates all the specifics that are being used. So I just throw these up there, not that I'm going to spend any time doing the calculations myself. Now, let me jump out of this into the EasyPower tools and let's talk about what's going on. So as I mentioned earlier, if we start a new one-line diagram, I'm in 10.2, and I can tell that because now I have this little bar at the top that shows me the list of windows that it's open, I have open at any given time. Used to be I had to pull down my window box, and now they're highlighted, as I said, on this little bar. If we start a one-line diagram, then I'm going to do arc flash on, and let's say it's a 480 volt system. Once I go into short circuit focus and look at my short circuit options, by default the tool is selected 2018 as my standard, and it's using integrated method as my calculation methodology. Now, I mentioned earlier, if I have an existing file that it doesn't invoke those particular parameters or constraints, and so if I go open a file that I've had before, let's kind of pick one out of my sample list, then it will retain the model that we've had in the previous, or when we set it up previously. So now when I go into my short circuit options, here this model was originally constructed with 2002 as the standard, and I could select, as I still can select, whether I'm using momentary current or integrated method. So even in the 2002 version, if I look at the instant energy, I'm going to calculate my instant energy and look at my arc flash results. I can change, and probably the biggest modification for these calculations is based upon what I've selected for this calculation methodology. If I use momentary current, which again applies a higher level of current for the whole time of the arc, then I get much higher results as far as incident energy and arcing current. If I apply the integrated method, then my instant energy falls, in this case was about 25%. And that varies based upon the voltage level and the currents involved. Now you can see, even in an older model, we had the ability to display the electrode configuration and whether or not I was in an enclosed structure or an open air, but it wasn't necessarily used in the calculations. If I now convert this to the IEEE 2018 version, the tool will take those into account. And if I have that information in my database, in which case I don't here, I have to get another example, it'll show those results here. So let me go find an example that I do have that. Now, to be able to predict what's changed or how anything compares to a pre-existing study, it's difficult for me to show any examples that illustrate that. You literally have to do it on each individual example you have to deal with. What I've constructed here is just an array of the different definitions of the equipment or the bus. By default, if we look at a switchboard, the defaults used from the library would be picked up as long as I have specified default. If I have designated this as terminated in a vertical box under my arc flash tab, I'm going to show, okay, user defined, this is a vertical bus electrode terminated in an enclosed box. So what I've done is set up each one of these. Here's vertical into a barrier, and so it would be this checkbox. And I'm doing this so I can compare the different results with the same instant energy. This is horizontal in an enclosed box. And then I have two open air. And once I've selected electrode configuration that's not an enclosed box, and I have either vertical or horizontal choices. So and I've set these all up to have the same current and trip time. So if we fault these buses, you can see I've got 20,826 amps across the board. And looking at my instant energy, you can see I have the default is 1 calorie. And again, it's the same as vertical box termination because they are the same designation. Into a barrier, I have about a 25% increase in radiation. Horizontal, there's almost a 2x, again, because this is coming straight out at the operator. In an open air, in a vertical method, I have less than 50% for what I had from the default. And if I'm on horizontal open air, I have roughly the same amount that I had in the enclosed box. Again, all this is designated by what I chose as the bus termination type and the orientation of the electrodes. And as long as I'm in the 2018 standard. If I go back to 2002 and the momentary designation and apply it, you can see these change, and for the most part, they're less conservative, I think is the way to put it, except for the vertical and a barrier. So this just illustrates the ability now to compare one against the other once you have your system designated. Now, obviously, this doesn't do me any good if I haven't designated the dimensions as other than standard in my electrode configuration. I also wanted to show in the library, the standard library, what the designation for the defaults for arc flash hazards. And now, based upon which standard I select, I have the new definitions as we describe them, and then the default gaps and the enclosure size, all of which can be modified or even insert your own custom enclosure dimensions. And if you need help with that, contact tech support, and they can deal with whatever the modification takes. Again, if we were using 2002, we're limited to the dimensions and the types of enclosures and the multiplication factor, because it's including the distance x. So this will be dictated by what we selected in our short circuit options. All right, one other thing I was going to touch on, and oh yeah, so let's kind of close out some of this stuff and go back to my one line. I did want to pull up an example that's included in everyone's installation, and it's another place to, if you will, play or make comparisons to see what the differences are. And frequently I use the smart PDC design because we have different levels of protection, and I can go in and do my short circuit analysis with the old system and the momentary current. And if we apply this methodology and fault the bus, we end up with momentary current at the half cycle fault if I end up selecting the integrated method. Now this is another nuance here. When we go to integrated method, the numbers go down as far as the total current, but this doesn't mean the bolted fault current is reduced. It means that the current at the last trip device that clears, that's the lowest current that bus would fall to. So realistically, as soon as we run out of motor contribution at either 5 cycles or 30 cycles, my integrated method current level will be less. So it's a little tough to get understand the difference between integrated as far as what gets displayed on the one-line diagram. All right, I think that kind of covers everything that we wanted to touch on. Like I say, couldn't exactly be comprehensive on the whole standard, but in fact the tool allows me to do comparisons between the new standard and the old and get a feel for how conservative my approach is and how it applies to the different systems I work on. We're running into a time limit here, so all questions will be answered via email. I will leave this open for another few minutes to collect anyone's inputs, and the list of questions and answers will be circulated to anyone that's registered for the session. By all means, use the question input box to make your entries. Thank you all for attending. Be sure to check the EasyPower website for upcoming webinars and the newsletter for regional training locations and arc flash workshops that will be potentially in your area. And I hope you all have a good day.